Morning everyone, my name is Ahmed Adel. I'm a teaching assistant and researcher at the German University in Cairo. Today I would like to welcome you all to my research presentation titled Cloud Computing Predictive Resource Management Framework Using Hidden Markov Model. This work is supervised under Associate Professor Dr. Amr El-Mouki. Despite the massive increase of computing capabilities of workstations, supercomputers, and the omnipresence of powerful servers residing in data centers, computationally intensive applications such as optimization algorithms and business intelligence still require high computational power. That is why the need for having more computational resources is on the rise. The elasticity characteristic in cloud and volunteer environments refer to the ability of the system to expand and shrink dynamically according to the fluctuating system loads. These environments also allows its users to have on-demand access on resources and deploy their elastic and scalable applications on cloud and volunteer platforms. However, this on-demand access and the aggregation of these resources comes with major challenges in cloud infrastructure. Some of these challenges are the resource heterogeneity, the fluctuating application loads, the non-dedicated nature of resources in terms of availability and performance, the dynamic and unpredictable behavior of resources which affects totally the load balancing between the resources. Thus, cloud and volunteer systems must deploy intelligent resource management mechanisms which adapts to the dynamic and automated infrastructure. One possible approach to deal with the trade-off between cost and performance is employing auto-scaling systems, which dynamically adapt resources according to the fluctuating application loads. The reactive systems react to system changes but do not anticipate the future changes in the system state. On the other hand, the proactive systems predict the future system behavior changes and adapts the resources dynamically to meet the future application needs. Auto-scaling systems depends on monitoring and gathering the real-time performance data of system resources. However, system overheads can result from this collection and updating of performance data of resources in a real-time manner. Thus, efficient resource management and auto-scaling techniques should be integrated to guarantee efficient use of resources. Some of the work have been done to address the challenges of load balancing in cloud and volunteer computing environments to maximize the resource utilization by integrating reactive and proactive auto-scaling systems. Also, prediction models based on the slide window scheme have been proposed to enhance and maximize the resource utilization. Also, some work have been done to address the problem of the dynamic resource states by employing prediction models based on backpropagation, temporal difference, and neural network, and prediction models based on Markov exchange. Although some optimizing approaches were proposed for tackling the challenges of auto-scaling and load balancing in cloud and volunteer computing, it's concluded that proactive auto-scaling systems are more efficient to anticipate the future system state. Dynamic load balancing approaches didn't consider the communication overhead. Approaches that maximize the utilization of resources assumes that the performance data of all the resources can be monitored and gathered non-intrusively. So, in the presented work, resource management and auto-scaling approaches for cloud and volunteer computing systems are proposed for performing efficient task allocation, balancing the load between resources, reducing the communication overhead due to data transfers, and finally enhancing the performance of the system and maximizing the overall system utilization. The system model is composed of several entities. In the cloud environment, the user entity creates a client application which contains a list of tasks along with its needed system and user requirements. This client application is submitted to a middleware agent, which is the resource broker entity, to be responsible for scheduling the user's tasks, interacting with the cloud core infrastructure, submitting tasks for execution, and finally sending back the results to its user upon finishing execution. For the sake of comparison, a conventional reactive auto-scaling algorithm is re-implemented from the literature. In this conventional reactive approach, the user submits a batch of tasks, which is the workloads, to its corresponding resource broker for execution. The resource broker gathers the capability information of all the resources in the system from the information service entity. This capability information is used to calculate the overall system workload. The calculated overall system workload is measured and compared against a threshold-based rule in order to take an appropriate action. In the conventional reactive autoscaling approach, it provides a solution for dealing with the cost-performance trade-off by dynamically adjusting the system's resources to satisfy the current workload. This approach meets the current system needs in terms of the overall workload and cost, but it does not take into consideration the workload balance among the resources in the system. Thus, a reactive auto-scaling task allocation approach is proposed to provide a solution for maintaining a balanced load between the resources within the system after auto-scaling is performed. In the proposed reactive auto-scaling approach, initially the resource broker will issue load request events to be broadcasted to each resource in the system, requesting their current real-time performance. Then the resources reply with the real-time CPU load, which is the log packet, to the resource broker, which gathers real-time system state for auto-scaling decisions. According to the ratio of CPU load, each resource will be mapped to a load state and a load number according to this table. The load number of a resource will be used for generating scores for each resource. All resources start with the scores equal to 1. After computing all the scores of all resources, the share ratio of the tasks assigned to each resource will be calculated using the values of the minimum and maximum scores from the list of all scores. Although the proposed reactive auto-scaling task allocation algorithm shows good performance in terms of load balancing among resources, however, the continuous broadcasting of requests responses before auto-scaling decision-making will cause communication overhead in the system network. That's why a hidden Markov model-based proactive auto-scaling task allocation approach have been proposed to provide a solution to reduce the communication overhead for requesting real-time CPU performance data from resources while preserving equal load distribution among the resources. The prediction model is based on hidden Markov model, which is implemented to predict the future CPU load state of resources in terms of the CPU utilization without the need of requesting them before any task allocation. Your computing systems. Hidden Markov models are well-known statistical models used to capture hidden information from a sequence of observed states. The hidden Markov model can be characterized by the following notions: sequence. The proposed hidden Markov model consists of 4 states, each one representing the CPU load state of each resource, and 4 observations representing the ratio of tasks assigned to each resource. This slide shows the comparison between the proposed proactive algorithm and the proposed reactive algorithm. Here we predict the hidden CPU load state of each resource in terms of generating and broadcasting load requests in order to ask the resources to send the real-time performance data. The performance evaluation of the proposed approaches have been tested and evaluated under different simulation setups and environments. The simulation environment is set up with the parameters listed in this table. All experiments and simulations were performed using GridSim toolkit. The performance metrics in our approaches are the communication overhead, the overall system workload, and the prediction accuracy. The proposed proactive approach have been tested and evaluated using different training versus testing data ratios. Prediction accuracy and the communication overhead are measured and calculated for each tested ratio. The simulation was run for 400 cycles in seconds, where the simulation environment contained 10 resources and a total number of 10,000 tasks to be allocated. This graph showed the prediction accuracy for the proactive auto-scaling task allocation approach for 50 to 50, 60 to 40, and 70 to 30, and finally 80 to 20 training data versus testing data ratio. This graph shows the communication overhead for the proactive auto-scaling task allocation approach for the same ratios for the training versus the testing ratio. After testing different training and testing ratios, it's observed that the ratio between training and testing data has high impact on the prediction accuracy and the communication overhead. The 70 to 30 and the 80 to 20 ratios have higher prediction accuracy, while the ratio of the 80-20 will cause higher communication overhead. Thus, the 70 to 30 ratio was chosen as the best fit ratio in order to have a trade-off between the prediction accuracy and the communication overhead. The communication overhead refers to the ratio of the overhead communicated load packet with respect to the total communicated data. This figure shows the percentage of the communication overhead for the reactive and the proactive auto-scaling task allocation approaches, which is evaluated when allocating fixed number of tasks in each cycle on different number of resources for a duration of 400 cycles. As shown in the figure, there is a significant decrease in the percentage of the communication overhead when comparing the reactive algorithm against the proposed proactive algorithm. This is due to that when running the reactive algorithm, the resource brokers request all the resources to send the runtime load data before any task allocation during the whole simulation cycles. However, in the proactive algorithm, this is replaced by predicting the load state of each resource. during the predicted cycles, which will have a significant effect on the communication overhead. It's also demonstrated that increasing the number of resources in the system in both scenarios increases the percentage of communication overhead per cycle, as the number of generated load requests and responses will get increased. This figure shows the percentage of the communication overhead for the reactive and the proactive autoscaling algorithms across different fixed batch sizes in each cycle, while having 25 resources in the network for a duration of 400 cycles. There is a significant decrease also in the percentage of the communication overhead when comparing the reactive autoscaling task allocation against the proactive task allocation, for the same reason mentioned before, and from the figure that increasing the batch size in each cycle will decrease the percentage of the communication overhead in both algorithms. This is due to that the overhead is dependent on the number of resources in the system, so increasing the number of tasks while maintaining the same number of resources will increase the volume of the communicated data, so the ratio of the communication overhead relative to the total communicated data will decrease. The overall system workload is the average CPU load of the resources, which refers to the total number of tasks in execution or the total number of tasks waiting to be executed by the CPU. This figure shows the overall system workload for 400 cycles in seconds when running the reactive autoscaling task allocation approach. As shown in the figure, the overall workload before performing autoscaling is fluctuating between 0.3 to 0.9, which indicates that the system is not well balanced. In other words, there might be deficiency or idle resources affecting the overall balance of the system. However, after performing autoscaling, the overall workload is fluctuating between 0.7 up to 0.85, which indicates efficient system utilization by adapting the system state either by adding more resources or removing resources. This figure shows the variance of resources of the CPU load when comparing the reactive autoscaling without scheduling and with scheduling. As shown in the figure, the variance when running the conventional reactive autoscaling algorithm versus the proposed reactive autoscaling task allocation algorithm, it's clearly observed that the variance is much higher in the conventional reactive algorithm, as the values are fluctuating from 0.2 to 1 compared to the proposed reactive algorithm where the values range between 0.2 up to 0.5. Whenever the variance is low, this means that the load between the resources is fairly balanced, while having increased variance indicates that there is an insufficient task allocation among the system resources. The prediction accuracy is described as the correlation between the predicted values and the actual true values. To evaluate the prediction accuracy of the proposed hidden Markov model-based approach, the resource state is predicted and compared against the actual resource state of the resource. This figure shows the percentage of the mean prediction accuracy for the proposed proactive autoscaling task allocation algorithm when allocating different fixed batch sizes across different number of grid resources for a duration of 400 cycles. The proposed algorithm can achieve high prediction accuracy between 86% up to 90% in almost all different simulation setups. The prediction accuracy didn't significantly change while increasing the batch size. This is due to that the prediction accuracy is dependent on the ratio of the assigned grid tasks to each resource from the total batch size regardless of the batch size itself. This figure shows the percentage of the mean prediction accuracy when allocating 25 tasks in each cycle across 10, 15, 20, and 25 resources. It's shown that increasing the number of the resources increases the mean prediction accuracy. This is due to that the average of all the hidden Markov prediction models of all the resources is calculated and used for calculating the mean prediction accuracy. This figure shows the percentage of the mean prediction accuracy for the proposed proactive autoscaling task allocation algorithm when allocating 10,000 tasks for random batch size compared against allocating fixed batch sizes. The figure indicates that the prediction accuracy quite decreases in case of random batch sizes when compared against the fixed batch size. This is due to that the hidden Markov model of each resource will visit more states during the training cycles, indicating that the behavior of the resources will be sparse and need more cycles to enhance its prediction accuracy. So, to conclude, this paper proposed resource management autoscaling approaches for performing load balancing while reducing the communication overhead in the cloud network. A conventional reactive autoscaling approach is re-implemented from the literature. This conventional reactive approach leads to inefficient use of resources. That is why a reactive autoscaling task allocation approach have been proposed to overcome the problem of load balancing between the resources. However, It achieves good load balancing between the resources. Communication overhead exists in cloud network. That is why a proactive auto-scaling task allocation algorithm have been proposed to overcome the problem of the communication overhead. The results show that the proposed proactive approach has a high prediction accuracy while reducing the communication overhead significantly. Here are my references, and thank you.